Hello everyone! I am excited to share with you a new technical breakdown of my Snowman VR project. In our last installment, we explored the pillar assembly effect, and now it's time to delve into floor destruction. We'll begin in Houdini, where I will guide you through my process of sculpting and fracturing the floor, configuring collision geometries, customizing RBD simulation, and running many of them using TOPS network. Then we will process impact data and export it using point cache, use vertex animated textures to pass simulation results into Unreal, and finally, all exports will be automated using Python. Then in Unreal, we'll examine how I set up the floor meshes and materials to drive the animation, configure Niagara particle system to add extra layer of details, and automate assets import using Python. Let's dive into it. We are in Houdini, and let's start by preparing the floor to simulation. Let's check our imports. We have an animated low poly pillar, which will hit the floor. We have a hit points where pillars are landing, and we have two collision geometries, chapel walls and seats. Now, if we look on the area around pillars, where pillars hit, this area is much smaller than the overall floor. And it would be great to reduce the fracturing of the floor and simulation to this local zone, so that simulation will run faster. And also we will get the lower poly count, which is important for us because the animation will be played in VR experience. So let's localize the simulation to this area, and around it we will put the static geometry. Our floor is quite thin, and we have two layers of it to have more debris flying around. Then we remesh to increase the resolution, add the UVs. Note about UVs, so we want to have a continuity of UVs between animated floor and static one, so that when we will shade everything in Unreal, we will not see a transition, right? So UVs of two geometries should align, which is what we have here. So to have them aligned, I'm scaling UVs of animated floor with the size of UVs of static floor. Then to get a bit more natural look, I'm adding a noise to point positions, and we are ready to fracture this. So my artistic goal was to have a chain of destructions. First, we break floor into those large groups, and when they hit the environment, they are further decomposed into smaller fragments. So to make this work, I only have the constraints within those large groups and no constraints between them. And the constraints are very strong initially, so that when pillar hits the floor, the small fractions stay in formation, but when they fly away from the pillar a bit, I relax the strength and allow subsequent collisions. To organize the constraints, I do two iterations of fracturing. First, breaking the floor into large chunks, and then into smaller fragments, plus adjusting the constraints within each. So let's look on details. The first iteration happens layer by layer. I'm scattering the hit points around pillars. Here is the result after fracturing. Those blocks on the side of the floor, they have this unnaturally looking straight edge, which I don't want to show in the game really. Rather, I want to keep those side chunks on their red positions, so they also serve as a transition between static floor and animated one. So to exclude them from further simulation and breakdown, I'm assigning them to the group and will exclude from further processing. Next step is to come up with the seed for every fragment, and this seed will drive the color variation in Unreal. And as we don't really need the constraints between those large segments, we can safely drop them. Then breaking into smaller fragments. See how I'm excluding this side group. Here is the result after second iteration of fracturing. The large chunks are split into smaller ones. Then assigning UVs for the edges of the fragments. Even though our floor is a single geometry, based on the part of it, we have a different colors. So the top is dark and insides are emissive, and the edge is a smooth blend between those colors. And to shade this properly in Unreal, for every vertex, we need to know which part of the floor it belongs to, if it's top or inside or edge. And one of the ways to pass this information is to use the vertex colors, which is what I am doing. Here is the result. So if it's the first layer and facing top, red is 1, so red is for top, green channel used for encode piece seed, insides have blue 0, and the alpha channel is remapped height. And the last piece for the floor geometry is to prepare the constraints. Right, so we have some original strengths of the constraints. For example, the maximum is 1800, and I'm scaling the strengths for all of the constraints on the first layer and half of the constraints on the second layer with some big number, and also keeping that scalar to later revert to original value. Right, so after scaling, the strength is much higher. And the next part will be about preparing the simulation. We will start from the pillars. So we copy our pillar to target positions, assign name and ID, and then, so right now both of them are landing together, and I want to land left first and then right after some time. So for that I'm using a chops, the simple network, to offset movement of second pillar. Then this is my way to prepare all of the collisions. This is the floor, a static floor around animated floor, again walls, seats, and pillar 1 and pillar 2. Next step is to do RBD configure. We have active for all of the parts of the geometry, but we set side, whatever is inside group, as inactive, and also the part of the floor that belongs to the pillar, second pillar, is also set as inactive and will be activated later in time, because we don't want to have it simulated when first pillar hits the floor. Next part is simulation. So our active objects are floor, pillar 1 and pillar 2. And note that pillar 2 is created later in time, because I don't want those debris to hit the pillar. It will not be visible in our experience, so we don't want anything to collide with it. And this, the frame number, it's coming from controller. I try to do everything procedurally, like length of the part is set in controller, and a lot of other things as well. Next one, we have a pillar break in the floor, but it's a bit hard to art direct where debris will fly. So in order to get some guidance, I am using those curve forces, and the curves are defined here. So around every pillar I'm having, let's look how it works. I have several zones on the sphere where I'm scattering the points. I'm copying those points around pillar hit zones, adding the lines, and those are my curves. Those are my curves that will drive the force. And I only want those curves active around some point in time. Again, it's defined in controller where when exactly those curves are active. Adding speed limit, drag and drag spin, and those two subsolvers. So first, I had some issues when chunks of the floor, especially on the second layer, were wobbling after the simulation. So pillar hits and they kind of continue to move and bounce around, and doesn't look very great. So to counter that, I'm tracking the distance traveled of every part, and if it's not moved far after some frame, I'm freezing it. It helps. It doesn't solve it completely, but it helps. And also when time comes, I'm activating the part of the floor for the second pillar and deactivating the floor for the first pillar. Then to have a dust emitted when chunks hit the walls or hit the floor, I'm collecting an impact data. Constraint network. So for constraints, we are computing how far the debris flew away from the rest point, and if they passed certain threshold, we are scaling the strands back by dividing on multiplier. Otherwise, I am keeping impact on the constraints as 0. Then we add gravity, and that's it about simulation. Now let's talk about evaluating different simulation setups. First, what's the motivation for scaling to multiple simulations? Why not to just have a file cache, change the parameters, and evaluate the result? Answer is efficiency. We have many different configurations of what can come into simulation. For example, we can have 2 layers of floor, 3 layers of floor, different height, different settings of forces acting in simulation, and then the parameters of the solver itself, like number of substeps is very important, and other ones. And some of those configurations will give better outcomes than others. So my task is to find the best looking ones, which is what I'm doing using tops. I'm defining the settings I want, run the simulations. I schedule many of them. So you can have multiple simulations. Evaluate the results, see how they are different, choose the best looking one. Then maybe you find some bugs or something you'd like to improve. Do these changes and schedule another run, and while the simulation is running, I can do something else in parallel. And this iterative kind of search process is at the core of how I build stuff. And Tops and Houdini is helping me. That's my latest setup. First, I work with floor geometry, define its fracturing seed, and save the geometry to disk. So for that I'm using a ROP fetch, and apparently to work with file cache, you need to set path to it and then /render. So this guy is referencing this file cache, storing the floor geometry separately from the simulation, because you can have single floor and then many different simulations using that floor. Then defining parameters of simulation and the similar ROP fetch for file cache, storing the simulation itself. Within sim, I'm getting the points that represent proxy objects and storing only those, quite packed and efficient way. And remember, we want to have an impact data to then render the dust when pieces collide with each other. So for that, I'm importing the impact data and setting not trigger simulation. It was also important for me to save impact and proxy points together, so that I'm using only one file cache and therefore single ROP fetch within top network. And for impact points, the impact data is actually a time series data for every frame. So it's kind of cumulative. On the last frame, you get the impacts of all of the previous frames. So it's just enough to go to the last frame and save data from there. Using RBD pack, it's not intended to be used in this way, but nobody can stop us. And that's it. Then rendering the floor geometry. Reading the cached floor, reading proxy points, transforming pieces, and getting this beautiful simulated floor. Now I'm also dropping not visible polygons. So the polygons that will not be visible in game are dropped for optimization purposes. Then this animation is exported using vertex animated textures. Pretty standard settings, except this guy, and exporting vertex colors. And then not only simulation we're exporting, but remember we have a static floor around animated one. So this is the cube from which I subtract the floor, and then I also add the bottom polygons of the animated floor, so that when debris are flying away, we, instead of seeing a flat surface, we're seeing more interesting texture, like here. Okay, then this guy. So before animation starts in Unreal, I'm showing the static geometry. It's much smaller than animated one. And after simulation ended, in the same way, I'm showing the static geometry as well. So the poly count is not small, but remember we have the procedural system and can tweak the settings. And anyway, it works nicely. I get a 90 FPS in VR. Now this export, like 3 static meshes, animated vertex textures, and then I will show you exporting 2-point caches as well for impact data and for trails. A lot of buttons to click. If you will go manually and click every button, save to disk, it becomes not very interesting. So for that I have an automation in my controller. I have those buttons. I can trigger the simulation, I can trigger the export, and I can trigger simulation and export. And underneath It's a Python code that goes over all of the nodes, FBX, VAT, point cache, and it's doing an export. The last part in Houdini is to render the data, to render the trails of the fragments. Right? Remember, each fragment has a trail after it, and then when they hit the floor or when they collide, we show this dust. So both effects are rendered using Niagara in Unreal, and the data is passed as a Houdini point cache. So for the trails, it's quite simple. You get the simulated geometry, you do a debrees source, define the parameters you want, points, density, and then add expected variables by Houdini Niagara plugin and export. So I'm exporting for the left and for the right pillar separately, because they will have their own, each will have their own Niagara system and therefore separate cache. Now for the impact data is a bit more tricky. So first we have a lot of data, 21 million points. I decided to collect as much as I could and then in post-processing drop everything I don't need. So first I drop by distance drop with low distance traveled. If the fragments stayed on their positions, not showing impact data for them, kind of immediately less points, then drop by low velocity, even less, and then fusing the points and also applying some mask fusion, so again even less points, and then transforming this just a static table into the time series. So whatever data is around this frame, I'm only having it here in the result. Again, adding expected variables and exporting for left and for right pillar. So that's it for Houdini, and I will see you in Unreal. The last part is to set up our effect in Unreal. Let's take up how it looks. The pillar breaks the floor, so those debris, those are driven by vertex animated texture we created in Houdini, and the trails after them is Niagara particles. So we will see how I configured this. And the second pillar. Boom. Nice. Right, so our animated floor is around the pillars. Remember, we have animated only this small part, this guy, and then around it we have a static low poly mesh. So because the UVs of those meshes align and the internals of materials align, we don't see a transition. Right. So checking the dynamic mesh. Now it's not tiny mesh, absolutely, but it's not huge either, and for this kind of hero effect, I think it's okay. The size is pretty much, it's not huge. And remember that our pipeline is procedural, the simulation is procedural, so if we need, we can reduce or increase the resolution as we want. Now with vertex animated textures or VATs, you drive the animation from material. I encourage you to check the SideFX tutorials on how to set up this stuff and how it works. I will only show how I'm using this. So this parameter display frame, it's how you control the playback of animation. You can change this parameter from the blueprint. For example, you can have a curve or you can calculate the frame manually. For myself, I have created the base actor, which handles, for me, all of the common operations I do with VATs. So for example, before we start the animation, we're showing, I call this pre-animation mesh. This is the low poly mesh we also exported from Houdini. It's very small, and we are not eating resources when we don't need. So when animation starts, this pre-animation mesh swapped with dynamic mesh. We can also swap in the end with post-animation mesh. Then I have the parameters to set up the playback. Maybe I want animation to be played backwards, like with pillar, and other things. Now the base class is in C++. A bit of C++ I will show you. So this update effect, we create a timer and trigger, invoke the method on timer, calculate the current frame, and set the material parameter. Quite simple. Now let's check the material. Having a bunch of parameters that define the look of our floor, but the material itself, it's not that huge, because I extracted as much as possible of the logic into functions. So recap, we want to reuse the logic and the way we shade the static and an animated floor. So in order to not duplicate the code, a lot of logic is extracted into functions. For example, we're getting and scaling UVs and adding the noise to UVs, adding a noise to internals of the eyes, getting normals. Here is how I'm, by the way, adding detailed normals into VAT texture, and then blending between top and inside colors. So right, the top is dark, inside is emissive, and this blend happens here. So our vertex color, its red channel stores the mask, which says us if it's a top layer or inside, and then the alpha channel stores the height mask. So we're using those channels, and the highest mask is used to shade this side of the chunk. Great. Now the material for the static geometry, again using all of those functions and passing outputs into material. And now Niagara part. So our ground destruction actor has a reference to Niagara actor, and when the effect is activated, we also activate the Niagara system. So Niagara, the system contains both emitters for the trail part and for the impact. We can split those into two systems, but having them together is easy and convenient. Now, to work with Houdini point cache from Niagara, you need to have this plugin, Houdini Niagara. You can find it on SideFX GitHub, and I also encourage you to check their tutorials on how to work with point cache. I'm using it slightly differently, so let's disable the impacts for now. This first emitter is reading from Houdini point cache. So if I enable the render it for it, boom, you see those are the same points we have exported from Houdini. We sampled them on the sides of the floor chunks and stored as a point cache. But I don't want to show those points in the game. I rather want to emit the dust from them, and it would look in result as a trail. So how to do this? Those emitters are also GPU emitters, because we have plenty of particles, and with GPU you cannot have events, you cannot have location events, but we can spawn particles from other emitter. It works just fine, what we need. Basically, again, this emitter is reading Houdini point cache, is reading the attributes, and then in this emitter we're spawning particles and sampling particle attributes and overriding, for example, position and color. So that's why I call this anchor and this one trail. And in the result, I have this stuff. Now, so we're sampling the particles, then adding some variability to location to have this curly trajectory, and add a velocity. And velocity is around normal. So again, from Houdini, we exported the normals. We have set them to look outwards from the sides. Then normals are red. In this emitter, then red from attribute reader. I'm reading Houdini normal and setting the velocity around normal. Also, we exported this guy called piece seed. This is the float attribute, and it's the same for the float chunk, but different across them, right? And again, we're sampling this piece seed and setting color based on it. And then the trail emitter derives the color from anchor emitter. With impacts, it's almost the same setup. However, I am taking this pattern kind of one step further. So impact points, they live for a short amount of time. So that's why I'm spawning, again, have an emitter which samples the point cache. Then I have another emitter that spawns the particles from those, and with impacts. This is the kind of anchors, if I will visualize them. Yeah. On the impact event, I'm spawning those anchors, and then we have trails which are sampling the anchors, adding all of the attributes, adding velocity, the same almost setup, and showing the impact. We've got to the last part of Unreal setup, which is actually the first part, is importing the assets from Houdini. So recap, we have plenty of meshes. We have animated mesh, static mesh around it, static mesh instead of animated, several textures and 4 Houdini point caches. And at some point, I had a lot of iterations in Houdini when I had every time go and re-import all of the assets. Just got really upset about that. So I added those Snowman automations. I just click the ground destruction and all of the assets related to ground destruction are re-imported. The same for build pillars. How this is set up. So in project settings, you can define the startup script. I'm defining, so this script will be executed on a startup. Let's go inside. So menu helpers. When script is run, we execute this method. To add an item to menu in Unreal, you derive from their tool menu entry script class. You override and execute. Within execute, I invoke my import logic, and this method is registering the menu entries. Right? Create an object, initialize, register. Import ground destruction. I define a list of meshes I want to import point caches, and also have a way to import everything from the folder, which works for textures. And in the end, it all ends up in this guy. Using Unreal Asset Tools helper to get asset tools, then automated asset import data, and importing assets, and Hopefully it's all imported successfully. That was the last part for our breakdown. Thanks a lot for staying till here, and it was a pleasure. Thank you.